Okay, in the last video we have discussed how to solve or how to identify an analytical solution for a coupled problem. Okay, now what we will do is we will identify how the phase portrait is going to be for a coupled system. Okay, but before that we will have a little discussion about this uncoupled problem. Okay, so for this uncoupled problem, so this is the system, right, and the evolution equation for x and y, and this is the solution by solving these two equations. Okay, now for the system, what are the eigen values? So for this system, the eigen values, since this is a diagonal matrix, for this system the A matrix is a diagonal matrix, so the eigen values are A and minus 1. Okay, and the eigen vectors are x and y, which means 1 0 is one eigenvector and 0 1 is another eigenvector, right? So now in order to make this picture, what we have considered is just this A value and minus 1 value, which means just the eigenvalues, right? Just with eigenvalues we were able to understand how the system is going to behave. Okay, so what we are going to do now is we are going to do the same for coupled problem. So we are going to identify the eigenvalues and eigenvectors, and then from the eigenvalues we are going to identify how the system is going to behave, whether the system is going to have a stable node or unstable node or saddle. Okay, we are going to understand everything just by understanding just by knowing what are lambda values or what are the eigenvalues. Okay, so let's see how to do that. Let's see an example. Okay, so right, so this is for the same system. Now this is one eigenvalue and this is the another eigenvalue, right? So for this eigenvalue, what can I say? So along one line, okay, which is this line, if my initial condition is going to be along this line, then is it going to go towards 0 or go away from 0? Actually, along this line it's going to go away from 0 because it's going to grow. The lambda value is positive. Okay, but how about for this one or for this one? Okay, if the initial condition fall in this one, then it's going to decay, right, because the lambda value is negative. So basically in one direction it's going to grow and in another direction it's going to decay and going to approach 0. Then what kind of equilibrium point we are dealing with? It's a saddle point. Okay, it's a saddle point, and that saddle point, the two lines, the two straight line trajectories, okay, where one is a unstable manifold, it's been called unstable manifold, which is along this line, and a stable manifold which is along this line. Okay, so now if we draw the phase portrait, so this is the vector 1 comma 1, and this is another vector which is 1 comma minus 4. So this is 1 comma minus 4. Okay, so along this one it's going to go away from 0, away from this point. Okay, so therefore we have a and remember one more thing, these two trajectories are straight line. Okay, so these two trajectories are straight line, and then along this straight line, which is one of the manifold, okay, this is an unstable manifold, it's gonna go away from 0, but here it's gonna go towards 0. Okay, and then if I'm going to be in this region, the initially since this initial condition is very near to this manifold, it will behave more like this one until it reaches here, and then it will start behaving like this one, and same goes for this one. Okay, so it will behave more like this one, it will have a direction of this one, and then it will go like this. And you could understand with the same logic of the other trajectories as well. Okay, so this is the phase portrait for this particular system. Okay, for the previous, the example which we have discussed in the previous video. Okay, fine. We'll discuss some more examples in the next video.